Okay, class, where we are now is to talk about the calculation of what we call the glomerular filtration rate. The glomerular filtration rate. Okay, let's review and see where we are. All right, going to the kidney, we have what we call the renal blood flow. That's the entire blood flow to both kidneys. Whole blood, formed elements, and plasma. We said that about 25% of the cardiac output actually goes to the kidney on average. That's far in excess what it needs for its metabolism, but since the kidney is a filter, then 4 times around ought to filter all your blood. Now, technically speaking, since the filter we saw and described at the glomerulus and Bowman's capsule filtered out all the formed elements, so really what we're looking at more is the renal plasma flow, which is the blood without the formed elements. Okay? The way we calculate the renal plasma flow, first of all, the renal blood flow could be calculated by doing flow studies, a renal arteriogram, cannulate the renal artery. So there are different ways this can be done that would get the renal blood flow. There are various ways, radioactive assays and things of this nature. The renal plasma flow, though, can be calculated by simply this. Doing this here and then spinning a hematocrit. You remember what a hematocrit was? The formed elements to the plasma. Spinning that, and then the renal plasma flow would equal 1 minus the hematocrit. 1 minus the hematocrit. So you take the renal blood flow and multiply 1 minus the hematocrit. For example, if the renal blood flow, let's say, was 1250, and let's say your hematocrit was 50%, then 625 milliliters a minute would be your renal plasma flow. All right. Now, we get to the big boy, the glomerular filtration rate. The key is of the plasma that's going through all of those nephrons at the afferent arteriole, how much is actually going into Bowman's capsule? How much is being filtered? Remember, we've said time and time again, you can't filter it all because you would have nothing for the efferent arteriole. So you will filter some, and then you'll have to let some go and catch it on the next rotation around. We said that the average glomerular filtration rate was about 125 milliliters a minute. Okay, that's the average. It can go up and down. And remember, we talked about controls to maintain a good GFR despite changes in blood pressure. All right. So then we have what we call the filtration fraction calculation, which basically is as simple as this. How much is filtered to how much could have been filtered times 100, a percentage. How much is filtered to how much could be filtered. So if we were doing that, let's say we took the 625 that we could have gotten here. Remember we said if the crit was 50%, we'd have gotten 625. We could then take 625 as our denominator and 125 as our numerator. 125 would be the GFR, 625 would be that. So if we did that, if we did a 125 divided by a 625, that would equal 0.2. So then we multiply it by 100, and that equals what? 20%. So 20% using that scenario would be the filtration fraction. 20% of the plasma going through would get filtered. 20% of the plasma going through would get filtered. Okay? All right, so that kind of sets the stage there so you can see. All right, now what we want to do is figure out how do you calculate the glomerular filtration rate. So that's where we are now. That's what this topic really is, this video. All right, I'm going to come here then, and let's see what I have here. The calculation of the glomerular filtration rate is probably the most important calculation in evaluating the kidneys in a non-invasive manner. Now, there are many invasive procedures you could use to evaluate the kidneys, but this is a non-invasive procedure that can be done in the doctor's office or clinic or wherever. The use of this calculation combined with evaluation of the blood creatinine level, we'll talk about, and the BUN. Now, we won't say much on BUN. BUN is called blood urea nitrogen. These two values here have a normal range. If these two values here, one or both, is elevated, it shows that the kidney is not functioning correctly. If one of these, so when we draw your creatinine and BUN in your SMAC profile, if those are elevated, then that points to some trouble there. Okay. All right. So then, in order to evaluate the glomerular filtration rate, we must evaluate a substance in the blood, here goes the key, that is only filtered and not at all reabsorbed or secreted. So we have to look for something your body has, body makes. Remember, we're looking at filtration rate only, not reabsorption or secretion rates. We want a substance that is filtered in the same amount as the fraction of the fluid going into Bowman's capsule on one pass through. See, what we did, we said about a 20% go through. Remember, we just did that using this kind of thing. But anyway, that's what we're looking for. So that means we would want, if this was the case, we'd want 20% going in, not 30, not 10. Remember, all the fluid cannot be filtered at one time, or there would be no fluid in the efferent arteriole. Here we go. Here we go. The best substance to fulfill these criteria is creatinine. But unfortunately, some is secreted. So it's going to be it's not going to be exact. All right. Now, let's key in on this word creatinine. So I want to come over here now. What we have is I want to talk to you about creatine and creatinine. Creatine and creatinine. In humans and animals, approximately half of stored creatine originates from food, mainly from fresh meat and so forth, some vegetables. We produce that. Now, creatine, go back to your muscle. Creatine was the second source of energy in your muscles, particularly skeletal muscles, cardiac too, but particularly skeletal, second means of energy after the ready available ATP. You had creatine phosphate. Go back to muscle. Remember, some people take creatine to get a little more energy. All right. In humans, only half of the daily is biosynthesized from 3 amino acids, these here, in the kidney and pancreas. The rest is taken in. So the stuff is transported to the skeletal muscle. The skeletal muscle, strangely enough, strange to me, why don't they make it? But anyway, it's not made in there. It's made in the kidneys, pancreas, and liver, and then sent there. But it's used there in the skeletal muscles. Creatine is a breakdown. Now, here we go. Creatinine. See, this is creatine. Creatinine is a breakdown product of creatine phosphate in the muscle. That product, it can be leaked out into the bloodstream. Okay? All right. And so, so other words, creatine leaked out could be broken down to creatinine in the liver. Creatine leaked out from muscles. As you exercise your muscles, you make little breaks in them. And then the liver could make this creatinine. Now, creatinine itself is eliminated totally pretty much in the kidneys. Totally in the kidneys. That's why they'll say if you're taking a lot of creatine phosphate, you could have kidney trouble because you could clog it up because how the elimination goes. All right. So here's creatine and here's phosphocreatine. Okay, type of thing. All right, creatine kinase. So with this just kind of talks about, you can look at it how it's made. But anyway, let's get back to the key issue. So the substance we would use would be creatinine. All right, now go to the next one. So how do you do this thing? All right, how do you get that GFR calculated? Blood is drawn to determine the creatinine level in the blood. Urine is collected to determine the amount of creatinine in the urine. Okay. Note, the best way is to collect a 24-hour urine sample. The patient collects urine for 24 hours and brings it to the lab. The urine is then tested for creatinine levels, in other words, the concentration of creatinine, and the volume over the 24 hours is divided by 1440. They'll take the volume, measure the volume, divide it, and that's the number of minutes in the day. So in other words, when you do that, you'll get it in milliliters per minute. You'll get it in milliliters per minute. They would have calculated in milliliters, divided the milliliters by 1440, and then you'd have milliliters per minute. Our bodies vary in how much creatinine is put out at certain times of day. Thus, the 24-hour averages this out. Unfortunately, most of the time, you just at a physician's office, you just go in the restroom and give a sample, and they just estimate how much it would be over the day based upon how much you get, which could be very inaccurate. And the other thing is, this may be the time where you put more creatinine out, and 3 hours later you would put less out. But this is the quick way to do it. Okay? So we go now to this. So what do we have so far? We've got a blood level of creatine because we drew blood, and we got a urine level. Okay? Now we go to how we plug it in the formula real quick. Now what we're doing is we're doing something we call the creatinine clearance to approximate the GFR. The creatinine clearance approximates the GFR. You see, because remember, creatinine, some is secreted, so it gives an approximation. All right, the way that the formula goes is creatinine clearance, which approximates the GFR, equals U times V over P. Let's look at it. U is the urine concentration of creatinine in the urine. It's the concentration of creatinine in the urine. Let's say we're going to make that in milligrams per milliliter. V is the volume of urine in milliliters per minute. Remember, we took the whole volume and divided it by 1440, which gave milliliters per minute. P, we drew blood, is the blood plasma concentration of creatinine. Let's say also in milliliters per minute, milligrams per milliliter. So creatinine clearance would be U times V times this. Now this would be in the denominator. So that would cancel out. So then the answer would come out in volume. It's because the answer is how many milliliters per minute. How many milliliters per minute. So that's essentially how we do the thing to get that GFR. And like I said, the GFR, when it comes right down, that calculation is probably the most done calculation when you look at the kidney. And when you combine that and look at the creatinine level in the blood plus the BUN, it gives a good idea of how your kidneys are functioning without doing any invasive procedure. So I hope you kind of understand that now. All right, we'll close here.